We'll now discuss structural isomers. So just to remind you, when we're talking about structural isomers, we're talking about two molecules that have the same formula, but there's going to be different types of bonds in these isomers. There are two cases that we're going to deal with in this video. The first is called coordination isomerism, and the second is called linkage isomerism. We'll begin with coordination isomerism. Coordination isomers will have the same overall formula. You're going to have the same number of each metal and each ligand present in the overall formula for the compound, but the ligands are going to be attached to different transition metals. They're going to swap places, basically, giving you different bonds. Let's take a look at an example. In this example, our set of coordination isomers is the following. This is one isomer, CONH36CrF6, and the second coordination isomer is CrNH36COF6. So let's go ahead and draw these Lewis structures for the two isomers and see the similarities and differences between them. I'll note before we begin drawing the Lewis structures that in both cases we have one cobalt and one chromium, right? One cobalt and one chromium. We have 6 NH3s, 6 NH3s, and 6 Fs. And so these two isomers have the exact same formula. It's just that the atoms are arranged differently here. We'll go ahead and draw out the Lewis structures and see that. So in our first isomer, we have as our cation the complex CONH36. So we'll write that out. And again, because it is the nitrogen that has the lone pair, it's the nitrogen that's forming the bond to cobalt, so I'm putting the nitrogen here right next to the cobalt like that. All right, that's our cation, and then our anion is CrF6. So we've got Cr, and then we're going to surround it with 6 fluorides. That's one isomer. And then the other isomer is the following. We're going to have now the Cr in the cation attached to 6 NH3s. That's our cation. And then the anion contains cobalt, and then that's going to be attached to 4 F- ligands. So here we have two different compounds. They have the same exact formula. Again, they contain the same number of cobalts, chromiums, ammonias, and fluorines, but the atoms are arranged differently. Right? Seeing the Lewis structure kind of helps you to see the differences here, right? The atoms are arranged differently, and you have different types of bonds, which is why we call this a type of a structural isomer. You have different bonds, because in the first case, you have a bond between cobalt and nitrogen, and in the second, you have a bond between chromium and nitrogen, right? Cobalt is bound to fluoride in the second isomer here, right? So it's different bonds that you have in these two isomers. That's why it's called a structural isomer. And we call this a coordination isomer because you're changing the ligands that are coordinated to each of the transition metals. In the first isomer, cobalt is coordinated to ammonia, and in the second, cobalt is coordinated to the fluoride or the fluoro ligand, right? And so you're changing what's in the coordination sphere for each of the two transition metals, and that's why we call these a coordination isomer set. There's another example of structural isomers that we can talk about here, and this is called linkage isomers. Linkage isomers can arise when you have a ligand that can attach at one of two different sites to the transition metal. For example, we can consider the different linkage isomers that you could have for the following complex ion. We're going to take a look at CO NH3 5 NO2. And just to give this a charge, I'll just say that this is +2. But it doesn't really matter what the charge is. That's not really relevant for our discussion of isomers here. Now, with the NO2- ligand, that's going to have the following Lewis structure. NO2 minus looks like this. We recognize in the NO2 minus ligand that you have two different types of atoms that have lone pairs, right? Nitrogen has a lone pair and oxygen has a lone pair. You cannot simultaneously attach at both because these atoms are not separated by two or more atoms in between them, right? We talked about that earlier. In order to have like a bidentate or a tridentate ligand, the atoms with lone pairs have to each be separated by two or more intervening atoms in order to avoid the issue of ring strain. So you can only attach at one site. But there's a big difference between if you were to attach at this site where you have oxygen versus if you were to attach at this site where you have the nitrogen. And that's going to give rise to two different linkage isomers. So we'll just go ahead and make the note here that you can attach here or you can attach here. I will say that you could also bond to the oxygen that has two lone pairs on it. And really, I mean, there are resonance structures that are possible for this ion. And so what you're really dealing with here is the resonance hybrid, but I didn't want to get into drawing resonance hybrids because it kind of makes things more complicated and it makes it harder to see the lone pairs. It doesn't matter, however, if you were to attach to this oxygen or this oxygen, because either way, the bond is between the transition metal and oxygen, right? That is different from if you're bonding from the transition metal to nitrogen. That's going to be where we get different linkage isomers. So let's go ahead and draw out the two different isomer possibilities that we have here. So for one possibility, what we would have is our cobalt in the center, and then we're going to put 5 amine ligands around it. And maybe what we'll do is say, what happens if the cobalt links at the nitrogen site? So if that happens, the bond will be between cobalt and nitrogen. And then we'll have the two oxygens here and here. I'm just going to clean it up a little bit. And then this whole ion has a +2 charge. That is one possibility. And that's going to be compared to our second possibility where instead we link to the oxygen. So we'll draw that out and see the difference between them. So we've still got cobalt in the middle and 5 NH3s going around it. And now when you attach to the NO2 minus ligand, instead of attaching at the nitrogen site, right? So instead of linking here, we're going to link here at the oxygen. And this is what it's going to look like. So O, and then N, and then another O. And then to complete the octet rule, we'll just do that. Okay. So that's another form, another structure that this molecule can take. And this again is considered a structural isomer because you have different bonds, right? One has a cobalt nitrogen bond and the other has a cobalt oxygen bond. We call these linkage isomers because the difference between them is the linkage site on the ligand, right? In one isomer, we're linking at the nitrogen, and in the other, we're linking at the oxygen. And so that's why we call these linkage isomers. Again, they're isomers of one another because they have different arrangements of their atoms, but they both have the exact same formula. All right, that concludes our discussion of structural isomers. In our next video, we'll talk about stereoisomers.